Good morning. I moved into an office next door and it's very small, and the chair is like very low and the desk is very low and very small. It's weird. Um, we'll make do. Okay, so today we're gonna start chapter 2. Chapter 2 and 2.1 is good morning. Is examining numerical data, which is where we're going to spend a lot of time this week, and then we'll move into categorical data, potentially on Thursday or early next week. Okay. So just as a little bit of review, though, because we'll need it, let me add a page here. Good. And I need lines because it doesn't. There we go. Okay, so just as a tiny bit of review, we talked about variables. That's going to be very important. So we talked about variables, and we talked about numerical variables. Oops. Uh-oh. Don't fail me now, iPad. Numerical variables versus categorical variables. Now we're going to focus. So today in 2.1, we're going to focus on how can we summarize and how can we visualize numerical variables. And then in section 2.2, we're going to summarize and visualize categorical variables. Okay. So in chapter 2, so in 2.1, we're going to summarize and visualize each type of variable. You'll notice that how we summarize things depend on what type of variable we have, and so of course it's very important to know what type of variable we have, and so that's a good place to start for sure. And so what was our kind of key to identifying a numerical variable? We said, well, if it makes sense to talk about the average, or if the average of something is what I'm interested in, then I'm going to call it a numerical variable. Okay. So if I would like, or if I would be interested in the average, which today we're going to start to call the mean. So the average, which is the mean. So in statistics, we usually use the term mean. Sorry, I see there's a lag here. Hopefully it'll catch up. And so usually we use the term mean, but now it's your job to link the two. So when I say average, you say mean. I say mean, you say average, right? And I use the two interchangeably, and it's usually I just choose whatever sounds better. Okay. Sometimes I say both just to emphasize now in the beginning. But if I would be interested in the average, which is the mean, the variable is considered numerical. And remember, that was your argument that you were going to make, right? If you have to argue why something is numerical, then you would say, well, because I'm interested in the average height or the average speed or the average age or whatever, right? And so that's your go-to argument. Okay. So today we're going to focus on numerical variables, right? Numerical variables are measurements. Oh, sorry, it's laggy. So numerical measurements, so height, speed, weight, age, those types of things. Okay, the reason we spend more time on numerical variables is just because there's a lot more that we can do. We can calculate things, we can calculate the average, we can calculate the standard deviation, which you may or may not have heard about before. Right, we can do those calculations, whereas categorical variables, we just have things in categories, and so there's limited things that we can do. Usually we just report the counts in each categories. There are a couple of other things that we can do, but very minimal in comparison to numerical variables. Yeah. And so let's start with we saw a scatter plot last day, and so kind of a review continued. But you know what I'm going to do? I'm going to call this the end of the review, like so. Okay, what was there? I just had the chat in the way. And so we talked about scatter plots, and so now we're visualizing the relationship between two variables. And so we've got two numerical variables. In this case, kind of a fun graph, we've got children per woman, which we're using as a measure of total fertility, and then the life expectancy in years. And I think, is it per year or something? Oh, is it per year? Yes, it is. 2011. Okay, so in this case, man, I'm blind. And so when we're looking at these numerical variables here, right, remember we talked about, okay, does it look like I've got some sort of general pattern here? Yes, it does. And so what does that mean for us? It means that do life expectancy and total fertility appear to be associated or independent? And so we said, well, they appear to be associated, right? There is a relationship. In fact, it looks like there's a kind of relatively strong negative relationship. Right, strong negative. And I'm going to throw the word linear in there. We're not going to come back to that for a while, but it's good to incorporate it now. Linear just says that it looks like a straight line, right? If I had to put a general shape to this thing, I would say, well, it looks like a straight line. And so that's what strong negative linear means. Okay. And then here, we'd have to go on the website, right? We can only see 2011, but what we would see, right, would need to visit website, but we would see that the relationship changed. Changed over the years. Right, so I encourage you to go check that out and just confirm that, but also to play around and just kind of have fun with some interactive graphs, right? And so Gapminder, they've got all kinds of world data, and so they're kind of a fun place to go and check out. Okay, so what we're going to do now is I'm just going to introduce just a couple of plots, but then we're going to settle in and we're going to focus on histograms. So there are lots of other plots that we could use, but we're going to focus on histograms later. So a couple of plots that we could use, one's called a dot plot. And so if we have one numerical variable, remember we're in the numerical variable section, so of course we're only talking about numerical variables, but then what happens is we've got these very see-through dots, but as we add more and more dots, right, then it gets darker and darker and darker, right, kind of like a heat map situation. And so what we want to do, right, even though this one's kind of hard to see, you'll know what I mean once you see a histogram, it's easier to tell. But here, right, darker areas tell me that there are more points there. Okay, so what we want to get to work up to is we want to be able to describe the distributions. And so here we've got GPA as our variable, our numerical variable. Okay. And so if we have to describe the distribution, one thing, and the reason I kept this slide is because when we want to talk about the distribution, we have to talk about three things. We have to talk about the center, the shape, and the spread, right? Or usually I do shape, center, spread, just sounds better. Right, and so to describe the distribution. So here, it's a little bit hard to tell. So I do shape, center, and spread is the order I do. So this is going to take a little bit of work, right? Just kind of to visualize this. And this is why I don't really like dot plots because they're kind of harder to work with. But the darker an area is, the higher the bars would go if you were to stack them all on top of each other, which is another example that's coming up, right? And so what happens is we've got kind of relatively thin data here, and then it's kind of increasing, 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 and then it might look something like this, right? Because the darker dots, right, show me that there's lots of points there. It's so wonky. That's okay. And so I think you get the idea. And so in terms of the shape, right, I would say, okay, there's a long tail on the left, and we are developing terminology for this, but we're just introducing the concept right now, right? And so when I talk about the distribution, we're talking about what this thing looks like. Okay? So in terms of the shape, I would say it has a long, a long tail on the left. It looks to me like I could probably just generalize it with one peak. So we're going to talk about the tails and the peaks for the shape, which is probably what you would end up doing intuitively anyways, right? If I asked you to describe this shape, right, then you would probably talk about the peak or potentially peaks if there's more than one. So long tail on the left with one peak. For the center, it looks like the center might be somewhere in this region. I've got this long tail, and so very few points, and then it kind of builds up to the center. So I'm going to say roughly 3.5, right? So center a little higher than 3.5. I happen to know, whoops, it's lagging. I happen to know that it's 3.59 from the actual data. And so, oh, why is it? I'll just wait for there. Right. And so here I'll say actually 3.59. Oh, wait for the lag. Okay. Okay. So I just happen to know that that's what it is. And so, and I think it's from this, oh, it's not. I thought it was from the following page, but I guess it's not. That's okay. Now, in terms of the spread, what we want to do is when we talk about the spread, sorry, then we're really just interested in kind of minimum to maximum. Okay, so roughly between 2.5 and 4. Now we know that GPAs only go to 4, so of course that's our maximum, right? But it is interesting that there are no GPAs less than 2.5. It is possible, right? But I'm assuming, but in this case we don't have any. Okay? And maybe I'll use green. So the spread is from the minimum to, so is roughly from the minimum to the maximum. You just want to have an idea of what some generally acceptable values are, right? So here, what we're saying with the spread is that, okay, a GPA from 2.5 to 4, perfectly reasonable, it can happen, right? Anything beyond that, we would investigate a little bit more. And so roughly 2.5 to 4. So what we're going to do is we're going to develop kind of more official terminology for talking about the shape and the center and the spread. Okay, and so I don't love how the mean is here. In fact, I'm gonna scoot this. I want to do the stacked bar plot first, and then we can talk about the mean. How about that? Do a little switcheroo. Okay, so stacked bar plot is exactly what we kind of ended up developing with our dot plot, right? We stack the dots instead of layering them, right? And so a stacked bar plot or a stacked dot plot looks like this. Again, not very common that we would use these. Okay. Not commonly used. Oops. We typically would use what we call a histogram first. We typically use histograms. Okay. But the idea is the same, so it doesn't really matter. But I don't like how these are kind of wonky, right? And so but what they've done is just stacked the dots, and this confirms the shape that we saw earlier, right? We saw that this shape kind of looks like this, right? Roughly. Okay. And so that feels good, right? And so what we're going to do is we're going to focus on histograms. And in fact, maybe I'll bump this mean one. It's going to get bumped way down. Oh, it's not going to work, is it? Doesn't want to do it. Oh boy. Oh boy. Okay, I'll just keep bumping it down, I guess. Dealing with this lag. Because I want to keep talking about just the shapes for a little bit longer. Okay, so histograms. Histograms are the most common visualization for one numerical variable. Or one numerical variable. And so histograms, they're just a little bit cleaner than those stacked dot plots, right? Because now we make, instead of stacking the dots, what we do is we make bins. Okay. So these are bins, and anyone between 0 and 10, and I don't really care, we'll talk about what the data is in a bit, but any value between 0 and 10, they're going to get stacked on top of each other, which creates the height of each bar, right? So on the side here, we've got the count or the frequency. It's usually what it's called if you make a graph or a histogram in Excel, I think, or at least many others. Okay, so we've got this data density graph, right? And so it's going to show us the distribution. Okay? And so histograms are especially convenient for describing the shape of the data distribution. Okay, and so we can set the bin width, and in the lab you'll explore how to change the bin width and how it changes the graph. But for now, right, we're just going to look at a couple of different options, and then that'll be good. And so here, these are what we call bins. So this is a bin, and this is a bin, and so on and so forth. So the bin width here looks like it's 10. And so the data the variable that we're talking about is the hours per week spent on extracurricular activities. This one over here, it's so tiny, but there is someone in the 60 to 70 hours per week category, which is either very luxurious or exhausting, I'm not sure. And so, right, but you want to keep an eye out for extreme values like that. Yeah. Even though it's relatively hard to see because they're so small. Okay. But so when we're deciding the bin width, okay, there's a fine balance between, okay, you've got your bin width is too large and it's collecting too much of the data and you're not picking apart enough of the detail. Whereas if you make the bin width too small, then you're kind of exaggerating small changes, right? Which is not something that you want to do. So in general, what you're going for is just a general shape, right? Once a general shape emerges, then that's a good bin width. And so here, this is bad, right? Basically everyone is in the 0 to 50 category. That's not very helpful. And then I think it's like 2 people were in the 50 to 100 category. So that's bad. This one, so here the bin width is 10, looks like. And so I'm going to say this one is okay. The reason I say is okay is because the next one has a slightly smaller bin width of 5, right? So here, the bin width is 10. Here, the bin width was 50, right? This one is great, and that was a bin width of 5. Okay, the reason I say it's great is because when I compare this okay bin width one of 10, then I'm seeing this general distribution. But when I decrease the bin width a little bit, so I make my bins a little bit tighter, then I see that, okay, there's actually quite a few in the 0 to 5 category, and then it's rapidly decreasing. It's also highlighting where these individuals are in these kind of more extreme values. Okay. Now, of course, the bin widths that we see here, are completely data dependent. So I'm not saying that a bin width of 5 is always awesome. In this case, the bin width of 5 is really good. Now this one, I would say it's okay, but too much detail. Right? We're looking for a general shape. Okay. This one, it's okay. I would use this. That's fine. But what you'd want to do is you'd have to do something like this anyways, right? To kind of generalize it, because you don't want to focus on the minor details. But it looks like the bin width here might be 2, 2, 4, 6, 8, 10. Yeah. Bin width equals 2. Yeah. Right, so you don't want to get bogged down with these tiny details, right? Because in general, yeah, it's increasing, decreasing, and then dropping off. So when we talk about the shape of a distribution, we said, okay, well, one of the things that I would probably talk about, well, was the tails, right? What do the tails look like? Do I have a long tail on some side? And then we said, well, what about the peaks, right? We could talk about the number of peaks. And so that's going to be called our modality. So modality, a mode is a peak in the data, right? Kind of most frequently occurring value is the mode. Okay. So what we're going to do is we're going to talk about, do we have a unimodal distribution? Okay. Or do we have two modes or multimodal, so more than two modes? Right, so we're just talking about the number of peaks. Okay. Or are there no apparent peaks, which would make the distribution uniform? Okay. And so here, just remember that we're talking about, let's say you, and I think that, yeah, I usually talk about a sheet. You throw a sheet on, and then you look at the general shape, right? You don't want to get too nitty gritty, but this author, she says, okay, in order to determine modality, step back and imagine a smooth curve over the histogram. So ultimately, that's what you want to be doing. Okay, imagine that the bars are wooden blocks and you drop a limp spaghetti over them, right? So it's not going to dip down into every little crease, right? But it's going to kind of smooth over, right? And so we drop our limp spaghetti on this one here, and it looks to me like there's a single mode, right? And so here this would be unimodal. Okay. You don't want to get caught up in trying to distinguish this as its own peak, because it's not, right? When you drop that limp spaghetti on top, it's just going to generally smooth out, right? Whereas this one here, I would argue that, okay, if I drop a limp spaghetti here, I get two peaks, right? Two modes. So here, this is what we would call bimodal. Yeah. The next one, and you want to kind of, well, like it says, you want to step back, and I usually say squint, right? You want to kind of pretend like, okay, I could probably smooth this out, right? But it would dip down a little bit, I would say. Okay. And so here, multimodal, right, arguably. And then if I do this one, it looks relatively uniform, right? If I just do this, right, it looks relatively uniform. And so it's a little bit tricky in the beginning when you're trying to distinguish these shapes. But what we're going to focus on are unimodal distributions. Okay. And so that's where we're going to spend our time, right? It's good to know that these other ones exist, but in general, you're going to be arguing that it's a unimodal distribution. So if the distribution is unimodal, then we talk about the skewness. And so that's going to be, then we talk about the tails. We can talk about the tails. So what I mean by tails is we have this, right? If we drop our limp noodle here, right? I've got a tail to the right. Now the term that we're going to use here is that it's right skewed or skewed to the right. Oops. Skewed to the right. You could also call it a positive skew if you want. And so, but the key thing is to remember that here, histograms are skewed in the direction of the tail. So here, skewed in the direction of the tail. So in this case, right, in the second histogram, right, if I draw this, right, I've got a little bit of a tail to the left. Oh, let it catch up, right? And so here, the tail to the left, which means that it's skewed left. We can also say, instead of right skew, we can talk about positive skew and negative skew. If you prefer to talk about positive and negative on the axis, then that's fine, right? I'll know what you're talking about, so it doesn't matter to me. But just be aware that either of those work. Whereas usually what we'll have is this kind of generally symmetric curve, right? So here, symmetric around the mode. Right, around the peak. Okay, nice. So this shape is the only one that we're going to focus on and is the only one that we're really going to be able to analyze in this course. Okay, and so this shape, we give it a name. So just like you recognize a circle, you recognize a triangle, you recognize a square, you recognize all kinds of things, all kinds of shapes, right? We're going to call this shape, the symmetric around the mode, we're going to call it the normal distribution. I'll reintroduce it, but it's nice to see it now because it's going to be such a major player in this course. Now, I capitalize the N because, well, not just because it was the beginning of a sentence, but also because it's a name, right? And so here, normal, this is a name. So often I'll capitalize normal just to emphasize that, hey, this is the name of the shape. Okay, and so a normal distribution looks something like this. Okay. And so we're going to talk a lot about normal distributions. So a lot hinges on being able to determine the shape of a distribution. And then we'll be able to talk about things like the center and the spread of the distribution. Ah, I knew it. Okay. Right. To describe a distribution, we said we would have to talk about the shape, the center, and the spread. So they're all linked together. When we're talking about the shape of a distribution, one of the things that we want to pay attention to are outliers. Okay. So here we've got just kind of one outlier, it looks like, right? And we could try to figure it out by the height of the bar relative to the distance between 0 and 5. I'm going to say there's roughly 2 outliers, maybe. It looks like, I don't know, it doesn't look like 1/5, but maybe 2 outliers here. Okay. So when you're talking about the shape, right, you would generalize this distribution here. Oops, of course, I'll draw it. My pointer's not working. Right, so it's skewed to the right with about 2 outliers around the 20 point. Okay. And so notice that it's always going to be skewed in the direction of the outliers, right, as well, because they make the tail. So same thing here. Here I've got maybe, well, it depends. I guess I don't want to get too caught up in here, but maybe that's 4, so roughly 6 outliers, potentially. Right. So a kind of a bigger group of outliers. Right, but that's fine. And so what you want to talk about outliers, which are extreme values. Now, outliers are always something that you want to consider. You always want to talk about outliers because in statistics, we're more concerned about those weird values. We rarely want to talk about, oh, everyone looks like this and who cares, right? We want to talk about, okay, these extreme values, where did they come from? Who are they? And were they data entry errors, right? That's one of the main things. Okay. So we can eyeball the center, right, from the distribution. We can say, okay, where would the balancing point be? Usually it's going to be at the mean, especially if we have a unimodal symmetric, so a normal distribution. So the mean, which is the average, is the most common measure of center for a unimodal symmetric distribution is the most common measure of center for a unimodal symmetric, right, which we started calling a normal distribution. Now, some notation. We're going to be talking about the sample mean. Okay, so remember in statistics, we take sample information, but we're trying to learn about the population, which means that if I take a sample average, what am I trying to learn about? I'm trying to learn about the population average, right? And so we need we need notation and terminology to distinguish between the sample information and the population information. And so what I'm going to do here is I'm going to add a page here. Okay. And I'll say we will have well, maybe I'll say we will need to differentiate between sample information we're going to call information from a sample. So things we've calculated from a sample, brace yourself, we're going to call it a statistic. Statistic. Okay. So we'll need to differentiate between sample information and the corresponding population information, which we're going to call a parameter. Notice here that we've got P and P, right? Population has a parameter, whereas S and S, so a sample statistic. So if it's a measurement from a sample, then we call it a statistic. So we'll need to keep track of those things. And it's on the previous slide, but I'll enter it here. So what we're going to have is our measurement, right? Because what I want to emphasize is that, okay, if the measurement that I'm interested in is the mean, then I'm going to need to have some way of denoting whether it's a statistic or a parameter, right? Because there's going to be a sample mean, but we're trying to use that sample mean to learn about the population mean, right? And so now I've got a statistic, right, which is from the sample versus the parameter, which is from the population. Okay. So we're going to need notation to differentiate between the two, right? And so what we're going to use as a rule is we're going to use X bar, okay? But anything with a bar over it denotes a sample mean, okay? So here, anything with a bar over it, over it is the sample mean, right? So that means that X bar is the sample mean of X. Depending on what textbook you read, you might see Y bar, right? But anything with a bar over it is a sample mean, okay? Which, remember that the mean is the average, making this what? Your average smiley face. Which I like. So, right, we're going to need to use a sample mean to learn about a population mean. So what are we going to use? Well, to denote that we have a population mean, what we're going to use is the Greek letter mu. Okay? And so here, this is the Greek letter, Greek letter mu. Okay? And just to kind of show you how to draw it. This was not a very good version, but it's kind of like a fancy M. Okay, and so you start low and then you make a little U. But if you prefer, you can just write MU, and that's totally fine, especially if you're typing, right? Because this is an online class, so some of your answers you'll need to type, right? I try to avoid having to type Greek letters and stuff because that's really annoying. But in general, if you want to type it out, you can just write MU, and that's fine. Okay, and so in general, we use Greek letters to denote parameters, right? Where parameters are measurements from the population. We use Greek letters to denote parameters. So going back to how we introduced statistics, right? Statistics, the study of statistics is going to be taking sample information. So we said we're taking sample information, but now more specifically, right, we're going to take a statistic. Okay. So taking sample information, which we can replace with the word a statistic. Right. So taking a statistic to learn about, so taking sample information to learn about the corresponding population measurement, or information if you prefer, right? But that population measurement is a parameter. In the case of a mean, right? In the case of the mean, right, we use X bar, the sample mean, X bar, to learn about mu, right? The population mean. So we use the sample mean to learn about the population mean, right? And so that's going to take some time to kind of sink in. And I'm going to keep saying it a ton of times. And what I know is that it sounds really obvious. Well, yeah, obviously. But then at some point in the course, there'll be a time where it clicks and you say, oh, okay, sure. Yeah, we take a sample information or a piece of sample information to learn about the population information, right? But it's going to be kind of slow and steady. So if I gave you a set of numbers and I asked you to find the average of them, what would you do? You would probably add them up and divide by however many items there were, right? And so we'll start there for our formula, but we don't really need the formula, right? So the sample mean, if I go back to the previous slide here, the sample mean denoted by X bar, we add up each of the values in the variable X, which means that we have N. So remember from last day, the sample size. So N is the sample size, right? You add up all your values and divide by N. Okay. Another way that we could write this is that X bar is the sum of all the X's divided by N. Now this is summation notation. Summation notation, where the sum of X, so this is a capital, oh, it's not pointing. There. This is a capital sigma. Okay, but it's called summation notation. And so what this is saying is it's saying add up all the X's. right? It's just a shorthand version of add up all the x's. Okay. So here, add up all the x's. I introduce it here where we know what to do, right? We know to find the average, I have to add up all the x's. And so it's a nice kind of segue into when we have to read summation notation to learn about other formulas that we're going to need to use. Okay. Now, if we had the entire population, then what would you do if you wanted to find the population mean? Well, you would do the same thing. You would add up all the values of x in the population and then divide by the population size, and then you'd have the population mean. Obviously, this isn't possible most of the time because we don't have the population. Yeah? And so what we're going to talk about is the sample mean is a sample statistic, right? And we're going to start calling it a point estimate. Yeah? Especially later in the course, we're going to talk about a point estimate of the population mean, basically meaning it's our best guess at what the population mean is. Yeah? And so here, we know, highlight all that, we know that, okay, my sample mean is not going to be perfect. It's not going to be necessarily exactly like the population mean, but it should be pretty close, right? We expect it to be pretty close. Okay? And so that's what we're going to leverage in statistics is we're going to say, okay, yeah, there is variability, right? If I released my sample and I collected a brand new random sample, so it's still representative of the population, well, then my sample mean would change a little bit. And so I know that, but it should hover around the population mean, right? So that's statistics in a nutshell. And so let's see here. Right. So there's going to be kind of a lot of notation to get sorted in the beginning at least, but once you have a handle on it, then you're going to be okay. Okay, so let's see here. Just as a quick, right, how would you describe, and I'm not even going to say the shape, I want to know the distribution. Because when we talk about the distribution, we have to talk about all three things, right? We have to talk about the shape, the center, and the spread, right? Kicking it up a notch. So how would you describe the distribution? Oops. Of hours per week. So I guess I didn't need to do that. I could have just read the whole thing and cross that out instead. The distribution of hours per week students spend on extracurricular activities. So now we have this histogram and we want to describe the distribution. In terms of the shape, I'm going to say it's skewed to the right, or a positive skew, because it's skewed in the direction of the tail. Skewed right. And I guess I could add that it's unimodal. When I say it's skewed right, it implies that it's unimodal because we only talk about skew when it's unimodal, but let's just add it here, unimodal. Why not? In terms of the center, right, I want to be a little bit careful because when I think about my balancing point, which is intuitively where your center would be, it would be kind of somewhere around 10, right? So even though I've got a good chunk of the distribution down here, the bars are quite a bit smaller, indicating less data, right? And so here I would put my center might be somewhere around here. Center around 10. when I'm describing the distributions, what you want to keep in mind is just rough approximations, right? Is it around 10 or is it around 100, right? Things like that, where it would change my view of this distribution, right? What's a common value? 10, okay? Which is, you know, if you're choosing between 9, 10, 11, it doesn't matter, right? Roughly 10. What I want you to think about is imagine that you're on the phone and you have to describe the distribution that way, right? And then it'll kind of simplify things for you. And so for the spread, I would say the spread is roughly between 0 and 70. Okay. You could add something like most commonly 0 to 30 or something like that. But remember, the spread, you're just getting an idea of what's a reasonable value. Okay. And so, so just rough idea, right? Somewhere between 0 and 70. Okay. So some common shapes that we have unimodal, we have bimodal, we have multimodal, we have uniform. Kind of a weird wonky looking uniform, but that's okay, which we've already talked about, right? But just to emphasize that if unimodal, we can discuss skew. Skewed to the right, skewed to the left. I don't know why these are so hideous, but that's okay. Right, skewed to the right, skewed to the left, symmetric around the mode. It's always good to be able to imagine what the shape of a distribution would be. And so I don't just want to talk about which one of these would be uniformly distributed, but I also want to talk about, well, what shape would I expect? Okay. And I'm going to lead you down this road. So just as a general rule, anything involving money is usually skewed, okay? And it's usually skewed to the right, right? If you think about salaries, most people make a small amount, and then there's very few people who make a high amount, right? Right, and so in general, money is skewed to the right. Okay. And so, but let's talk about the weights of adult females. Now, it's kind of a phenomenon that things like weight and height and all these things, any sort of measurement, usually they follow a normal distribution. So I'm just going to tell you that it usually looks like a normal distribution. Okay. Normal distribution. Okay. I'll say that in terms of money, money is usually, right, I'll put money in quotes, is usually skewed right. Just as kind of a jumping off point. So when we talk about salaries, right, then you want to check in, does it make sense to make it skewed to the right? Yes, it does, right? Kind of a bummer, but most people are down here, right? Could be relatively high, but then we've got these very few with very, very high salaries, but there is a minimum as well, right? House prices, same thing. Most homes are in this this kind of general range, right? Pretty expensive in Kelowna, but right, but in general, and then there are some homes that are very, very, very pricey, right? But not very many. Okay? And so that's what you'll see, is that anything that has to do with money is usually skewed to the right. Now, what about the birthdays of classmates? Is there a reason to think that when we talk about the day of the month, right, that it would be anything but uniform? Probably not, right? There's nothing that says, oh, well, I know that most people are born on the second of the month. That's not a thing that we claim to have. And so what we would say is, we would say that this would probably be a relatively uniform distribution, right, across the day of the month. Right? Relatively even. The first, the second, the third, the fourth, the fifth, right? Doesn't matter. There's no higher probability of being born on a certain day of the month. I'm sure there's like minute probabilities that we could look into, but not in this case. Okay. So for this one, if we had more time, I would spend more time here, but we've done so much work here that what I want to do is I just want to summarize. Okay, so it's an application activity, and so sketch the expected distributions of the following variables. It's very similar to what we did, right? The number of piercings, the scores on an exam, IQ scores, and then come up with a concise way. So this is where I'm going to focus 1 to 2 sentences to teach someone how to determine the expected distribution of any variable. So what we want to do is we really just want to right, think about the shape, think about the center, and think about the spread, right? And that's going to determine the entire distribution, right? And so here we want to talk about the shape and the center and the spread. And what you want to do to describe these distributions, right? And I'm kind of changing the question a little bit. I'm talking about describing it, maybe not teaching them how to determine the expected distribution, but let's say describe, right? Because that's where I'm going to focus, right? On test 1, I'm going to ask you to describe the distribution. And so, of course, that's something that we need to be able to do. And so here, imagine you are describing the distribution over the phone. Kind of 90s style, you're laying on your bed with your shoe phone. Hey, I'm looking at this distribution. Yeah, no, it's normal. Yeah, normal distribution. Oh, it's centered around 20. Oh, between normal values would be between 0 and 50. Okay, bye. Right, and then you've described the entire distribution, because what would that distribution look like? Well, I said it was a normal distribution centered around 20 with values roughly between 0 and 50. It's the one I described, right? And so now I know everything about this thing, or roughly, the general distribution. Okay, good. So in terms of so we've talked about the shape. We've talked about the shape a lot today. We've also talked about the center. Now, the center for a normal distribution, we said, would be the mean. And there are centers, other centers that we'll get to next day probably. But if we have a normal distribution, then one measure of center that we can have is the variance. Okay, so if the distribution is normal, yeah, one measure of center, or sorry, of spread, right? Because here we were just approximating the minimum and the maximum, all right? But if we want an actual measure of spread, is the variance. The variance is roughly the average squared deviation from the mean. Okay, and so we get this very nasty looking equation, which we're going to break down. Okay, and so let's see here. The variance, the sample variance, is denoted by s squared. Okay. So s squared is the sample variance. Okay. And so what I want to do is just focus on this xi minus x bar bit for just 1 second. And I'm going to copy this onto a new page. Okay. So first thing I want to do is I just want to focus on x subscript I minus x bar, and just ignore everything else for a little bit. I'll put brackets around it. Okay. So what this is saying is that from each value of x in your data set, subtract the mean. So the first step would be calculate the mean x bar, right? Step 1, find the mean of x, which is x bar. Okay. Now, just to highlight what this would look like, right? X in your data set would be something like this: x1, x2, x3, x4, all the way down to xn. Okay, so here's what your data looks like. And we generalize the variable name by x, right? A generic value of x. And then we have x1, x2, x3, x4, x5, all the way down to xn. Okay, and so first thing you're going to do is find the mean of x, which is x bar, right? You're going to add these up and divide by n. Okay, then your second step, step 2, is subtract the mean from each of these x's. Okay. Now, I'm not concerned about you being able to do this calculation because we've got software to do it. There are online calculators, so that's not the point. The point is to illustrate why it's a measure of spread. Okay, and so here, when we take the distance from each point to the mean, what are we doing? We're seeing how spread out these values are around the mean, right? And so that's what makes it a measure of spread. Okay, and so here, from each data point, subtract x bar, right? See how far from the mean each value is. Okay. So then the next part, and what you're going to notice is that we always just build out kind of like an onion, right? So we move out from the very center of this equation. And so now I have xi minus x bar squared. Okay. Step 3, right? So now you would have potentially a new column where you've taken x1 minus x bar, x2 minus x bar, x3 minus x bar. I'm going to make you do it in Excel, not by hand, but using Excel. And so, right, in the lab. Okay, but now what are you going to do? You're going to have a list of values still, right, of the deviations from the mean. But now what you're going to do is you're going to square those deviations. Okay, so square each deviation. Okay. Now, when I square something, right, it makes it positive, right? And so now what we're doing is we're taking negative deviations, right? So the deviation is the distance from xi to x bar, right? And so then we square each deviation, which makes negative values positive, right? Squaring something has that that property. Another thing is that it also amplifies large deviations and amplifies large deviations. Okay. So that's it's just a fact, it's what we do. Okay. And so now what we're going to do, this notation here, though it looks scary, it is just summation notation, which means what? We're going to add up each of those values. And this here, you can ignore. The I equals 1 to n is just saying that, okay, do it from I equals 1 all the way down to I equals n. Okay. And so it's just notation. From I equals, I'll put it properly here, I equals 1 to n of xi minus x bar squared. Step 4, add up all the values. Or maybe I'll call them all the, what are they? Squared deviations. Nice. And then once you have that number, so this is just going to be a number, right? Then we divide by n minus 1. And there's a lot of theory going into why it's n minus 1 and not n. And it's also the reason why it says the variance, oops, I'll let it catch up. The variance is roughly the average squared deviation from the mean. Well, it's roughly because we divide by n minus 1 and not n. But it just gives us a better estimate. Okay, and so that's a fact and not something that we're concerned about in this course. So then here, overall, we have the sum from I equals 1 to n of xi minus x bar squared divided by n minus 1. So step 5, divide by n minus 1. And that's going to be our s squared, which is our variance, not n. And that's, for us, it's just because n minus 1, or maybe we use n minus 1 instead of n because it gives a better estimate. It gives a better estimate. But for us, we just need to accept it as fact. Yeah. And so now the variance is s squared. And so that's why the variance is a measure of center. Now, the more common measure of center that we use in this course is going to be the standard deviation. Okay, so in this course, the more common measure of spread will be the standard deviation. But don't worry, the standard deviation, which we're going to denote by SD, or in calculations, denoted by S, a lowercase s, oops. S is the square root of S squared, which means that the standard deviation is the square root of the variance. So that's kind of fun. So once you have the variance, you can take the square root, and then you have the standard deviation. And I think that that's a good place to stop for today. Let me just confirm here. Right, and so if we have a data set, usually we'd have the data here. Looks like we have it here. All right, then we can find the variance, but often we'll use a calculator. Right? One of the problems is that the units are squared, but we'll talk about that next day. Okay. If you have any questions, let me know. Otherwise, I will see you on Thursday. Let's stop this.